The direct labor cost is a little more complicated than direct material cost, and that's because when people enter the equation, there's a lot more variation in terms of their performance and behavior. Well, when we think of an operation, ideally we see the unit cost here on the y-axis versus time. The unit cost is decreasing, and the reason why this is occurring is that the cycle time is decreasing, and therefore the labor content per part is decreasing until we reach some theoretical minimum cycle time, and therefore the unit cost, the amount of labor content per part, does not decrease. So you can already see things are a little complicated in that the unit cost will change with time because of this change in cycle time. So that's significantly different than what we saw with the direct material costs, which was primarily affected by the scrap rate. Some of the factors involved here include the wage rate, where we are paying an operator for standard time. And as you know, standard time can include an allowance where we factor in variation between operators and add additional time so that all operators can be accommodated. We might also have this incentive rate where we make payments to operators who outperform the standard time. And another way of incentivizing the operators would be to provide a bonus if we can reduce the standard time. So essentially we are buying a reduction in the standard time, which represents a one-time payment for that reduction, which is consistent with what we just saw in our curve. Again, our operation time in terms of cycle time is decreasing, which is consistent with reducing our standard time. In order to estimate direct labor costs, we'll have to define a few more variables. First of all, T sub S is going to be that standard time for an operation. Again, I want to emphasize that includes some allowance, as opposed to the actual cycle time. So T sub C would be the expected cycle time based upon what we know about that operation. So we think of T sub S as being strictly greater than or equal to T sub C. Factoring in rework, we are going to have a certain amount of time associated with that rework. And we've already seen the production volume X going into our processes. Now we have E, the actual time that we're going to pass through in order to produce that number of parts X. So we express this in terms of hours to produce or to put X parts through our system, producing, of course, N good parts. R sub W will be our standard wage rate. Again, this number is readily available because we know exactly what we're paying, and we could factor in different grades of pay by taking some kind of weighted average. In addition, we might be paying an incentive piece rate in terms of dollars per part for beating that standard time, and that we will use R sub I. Again, that is well known. S, we already know how to determine S, and R, the fraction of defects that can be reworked successfully. So we've added a few variables based upon the parameters associated with operators and some of the dynamics, T sub S and T sub C, associated with timing in our process. And we'll see these parameters later on as well. So the simplest thing to do is kind of break this down because it is a little more complicated, and first look at the simplest component of our direct labor costs, what we'll call the base labor cost. So the base labor cost will essentially estimate the cost of the production time. So if I look over that time horizon, E, what am I paying for that time in terms of operators? So it's really the cost incurred as long as we are running that line, as long as we don't shut it down or that's the end of the shift. So R sub W is the rate at which we're paying one operator. Of course, if you have multiple operators, we would have to multiply that by that number, times the length of time that the line is operating. So that's a very simple estimate of the base rate. But now it becomes a little more complicated if we are paying an incentive piece rate. Now what makes this complicated is that you are only going to pay for good parts. Because if you incentivize to pay for bad parts, then of course your quality is going to suffer and your scrap rate will increase. Now you'll only pay for good parts when the cycle time is less than the standard time. That's the whole point of an incentive rate. You are trying to outperform standard time. So if I look at what I'm expecting to produce, I take my time horizon, times 60, I'm converting to minutes here because my standard time and cycle time typically are in minutes. And then I'll divide through by the time per part. Now note this is standard time. This is what you are expecting. The units on standard time, time per part. So you can see if we divide time per part into the number of minutes, we'll end up with the number of parts in time period E. Now out of those, we already know that we are going to produce 1 minus S times X good parts. Again, X being the number of parts that are going through our process. So what is the difference between those two? Well, we expected this number, and we are putting through this number in terms of good parts. Therefore, if this is greater than 0, what we're saying is we exceeded expectations. Because 1 minus S times X is what we need to produce, and this is what we actually produced. Note that we're only considering good parts. So what we'll end up doing is paying an additional amount based upon the incentive rate for this differential. Again, emphasis on that difference has to be greater than 0 because we are only paying for good parts. So I might make a lot of parts here. If these are the good parts, then of course, if this is negative, we're not going to pay out incentive. So the operators are given some incentive to decrease S, drive it towards 0, and also to outperform the standard time. Again, driving that towards the cycle time. Then we have the rework cost. So what happens when we can do rework? For those parts that we can do rework, we'll incur that additional cost. And so we will take our, this should be R here. We'll take our parts that are going to rework, RSX, and then multiply by the cost of rework, which will essentially be the time in rework, which will be different. We're not saying that T sub R is equal to cycle time because it's not. Typically it's significantly longer. So we take the time times our wage rate, which we had from before, and then we're going to multiply by the number of parts that are going through that, and of course we need 60 because R sub W is per hour, T sub R is in minutes, right? So dividing through by 60 will ensure that we have consistency in units. So now I've got my cost for putting through RSX. Note that this is not cost per part. Okay, so don't confuse that because we're saying that we're putting through RSX parts. We haven't got to the cost per part. We can put the three together and come up with the total direct labor cost. Again, the total direct labor cost to put those X parts through the process. We have three components. The base, we saw that was a very simple representation of paying for the time that the operators were on the line. Then we had the incentive, which was more complicated in that we had to take the difference between the good parts and the parts that we produced in that standard time frame. This notation here, the max, ensures that we're either 0, because this could be negative. If it's negative, then it'll be 0 times R sub I. If it's positive, then we will be paying incentive. Lastly, rework. Rework factored in the parts that are going to rework, the time it takes to rework, and multiply that by the rate at which we are paying for that rework. Note that this is the cost to put our X parts through the system. It is not the cost per part. In order to get the cost per good part, we have to go back to our factor, which, if you recall, we have n good parts that we are producing, and so we'll take that total cost from the expression we just came up with, and we'll divide through by that number of good parts. So this is the cost per part. In terms of direct labor. Well, we already know that n, based on our process model, is the same as 1 minus R times S times X. So all I did here was substitute what we already know about n in the denominator. And you can see the reason why. It should be R. Because my X will cancel out here. And then we'll divide this value E by X, also here. And of course, X is going to cancel out here, so it no longer appears in this expression. Well, if I look at this average actual cycle time, that T sub C, what is it? Well, essentially, it is our time frame. We're looking out over some period of time, and we are putting X parts through our system. So we can estimate this average cycle time by taking the time frame divided by the number of parts, both good and bad, and then of course we're going to normalize because E is in hours, so we'll convert it to minutes. So now I've got cycle time in terms of minutes. Well, we can rearrange this expression to find E in terms of that average cycle time and X, and then we can substitute that into our equation here where we see E divided by X and simplify that. So my question at this point is T sub C the theoretical minimum cycle time? You should be able to answer that question. Well, by factoring in that expression we had here, and let's just rearrange that to make it clear, we've got E over X divided by X is equal to T sub C divided by 60. So what we'll do is take T sub C divided by 60 and substitute that in our expression here everywhere where we see that, which we've got two instances of that. And that's what we have here. So as you can see, I've got my base rate in terms of the cycle time, again the average cycle time. I have my incentive rate based upon this ratio of cycle time. We'll come back to that over standard time. And this hasn't changed in terms of rework. Of course, I'm multiplying by 1 over 1 minus R times S, which you should know the meaning of at this point. Well, let's take a look at what we've got now, because now it's a little simpler. We've got 1 minus S here. What does that represent? That represents the fraction of parts that are good after going through the process. And then the difference between that, and of course if this is a fraction, it's between 0 and 1. And then we look at T sub C over T sub S. Now, does that make sense? Well, if I look at that meaning, T sub C is supposed to be less than or equal to T sub S, because we have that allowance in the standard time. So if it's equal to T sub S, then this fraction will be 1. And if this is 1, then of course this will either be negative or 0, and we will not pay out any incentive. So that is consistent with the role of incentive, because we're trying to beat the standard time, and we want T sub C to actually be less than that. So let's say that T sub C is less than T sub S. So now we've got a number here that is less than 1. Let's look at the other term, 1 minus S. We're not going to pay for bad parts. So we need this term because essentially this is incentivizing the operator to make good parts. Because if the scrap rate is high, then 1 minus S will be greater than this fraction. Or, sorry, if S is high, it'll be smaller than this fraction, and therefore we'll have a negative value for the difference. So you can see by incorporating the difference here, we've taken into account the incentive to have a better scrap rate, as well as the incentive to reduce the cycle time below T sub S. So the expression does seem to make sense. Now, what happens if you'd like to reduce that standard time? We said that we could provide a bonus, and that bonus could be a one-time payment to get a reduction in our standard time by some percentage. For simplicity, we'll just say that the bonus occurs at the end of a period, and we'll define a period as a year. So at the end of the year, if we decide to pay this bonus, then we can reduce the standard time and make it closer to T sub C. Of course, let's see what the effect of that is on our expression here. If we make the standard time closer to T sub C, then we will pay less incentive. So when you're thinking about paying that bonus, what you're really trading off is, do I have an incentive cost that is significant? And if I do, then I might want to pay that bonus to reduce this component of the direct labor cost. So let's see how we would factor that bonus in. We'll say that B sub C is the cost per part for a given year. And essentially what we're doing here is spreading out the bonus, because remember it's a one-time payment, over all the parts that are affected by that cost. So we're looking into future production. And then we're going to pay the actual bonus at the end of some period, I, and it could either be 0, no bonus, or some dollar amount. All the parts we produce after that period will have this additional cost. Now, of course, we're going to factor in the time value of money, as you know from engineering economy, so we could bring everything into present worth dollars. We already know that we have a certain amount we have to produce for customers, and that's going to be the required production volume in period J. We'll have n total periods that we'll consider, and therefore we have a time horizon. Now we need to be careful here, because whenever you have a time horizon, there's a lot of uncertainty about the future. And you should be able to identify that uncertainty here in the variables we've just defined. If we think about future production, the future production volume is really unknown. So we might have some estimates based on forecasts, but typically those are fairly crude, and therefore we could have a significant change in N sub j. If that's the case, then you would want to do some sensitivity analysis in which you vary the value of N sub j and see what effect it has on your overall cost. If it's not significant, then of course we're not going to worry about it. Well, here's how we calculate the cost. It's fairly simple. We'll take all future production going forward. So we go from period I plus 1, and the reason why we do that is that we are paying a bonus at the end of period I. So now we're looking at the next time period, and only the production, only the n sub j's that occur in that future time period. We add that up in the denominator. And then we divide that into the bonus that we're paying in that period I. Of course, we might be paying multiple bonuses over the entire horizon, and so we have to add all those contributions from each bonus to future production. Once we calculate that, don't forget that B sub C is the cost, the bonus cost per part. So I can just modify the previous expression. Note, of course, we don't put this in the numerator because the way we calculated B sub C was that it was only for the parts that are going to the customer. So that's already factored in. So I just add it to the previous expression, and now I have my direct labor cost including bonus. Don't forget that this is not necessary. In other words, it may be 0, but if we have significant incentive costs over time, then we might consider paying that bonus and getting a reduction. So the key concepts in the direct labor costs included cycle time, which hopefully you understand that time interval, standard time, which included some allowance, the incentive rate, the rate at which we're going to pay for good parts that outpace the standard time, and then finally bonus, in which we're going to try to reduce that incentive money that we're paying out. So in summary, we've got different components of the direct labor cost, including the base labor cost, the incentive cost, and then possibly a bonus and the rework cost. The direct labor costs are expected to change over time as the processes improve, and that is in terms of S, the scrap rate, as well as T sub C, the average cycle time. Don't forget, scrap rate, according to our expressions, plays a major role in the cost estimates, both for direct material as well as direct labor costs.